Good morning. Today we are going to work with the synthesis of hexaphenylbenzene. This is the scheme for the synthesis. This is the step of the pathway that we are going to work in today's experiment, which corresponds to the chapter 41 of your book. This is the final reaction to make hexaphenylbenzene, and it involves two different periocyclic reactions. The pericyclic reactions includes cycloaddition, electrocyclic ring opening or ring closing, sigmatropic rearrangement, and kilotropic exclusion. In this sense, Woodward and Hofmann received the 1965 Nobel Prize in Chemistry for working out the rules to predict and understand pericyclic reaction. The rules are now referred to as the Woodward's and Hofmann's rules. This is taught in advanced organic chemistry courses here at YouTube. Here are some examples of pericyclic reactions. The cycloaddition, you can see here an example of cycloaddition named Diels-Alder reaction. And in here, the pink arrows show the electron pair movement. Also, we have the electrocyclic ring opening and also ring closing. And in this case, the green arrows show the rotation around bonds. Also, the sigmatropic shift, in which we can find an example that is named Cope rearrangement. And finally, the kilotropic extrusion, which we are gonna see in detail in today's session. The hexaphenylbenzene synthesis combines two pericyclic reactions. First, the Diels-Alder cycloaddition, which involves the reaction of the diphenyl acetylene triple bond and our previously synthesized compound, the cyclopentadiene. This will form the corresponding six-member rings compound with a carbonyl group taken out to the 3D dimension. It means in a perpendicular plane, or ideally not in the same plane of this ring over here. After this, the kilotropic exclusion is going to take out that carbonyl group and form ZO carbon monoxide and form the product, which is the hexaphenylbenzene. Here we can see the molecular orbital theory calculation of the Diels-Alder cycloaddition, in which we can perfectly see how the precursor, which is the six-member rings molecule that contains the carboxylic group, the ZO group here, approaches the diphenyl acetylene, and as a consequence, we generate the six-member ring new molecule with the further ejection of the CO to generate the hexaphenylbenzene in the second reaction. Here is the calculated reaction coordinate for the cycloaddition reaction. As you can see over here, the activation energy is 46.3 kilocalories per mole, and the reaction is exothermic, as you can see from the difference in energy or heat from the reactant and the product. This green arrow determines the the exothermicity of the reaction, which is minus 13.1 kilocalories per mole. In this point, we need to highlight two important key aspects of the reaction. Since the activation energy is high, it means that this reaction must be heated quite a bit in order to initiate the reaction. In order to break the activation energy and to react, to further react and form the products. And the exothermicity means that the reaction is favored in this part after the activation energy is raised. The reaction is favored and will generate heat while the product is being formed. Here is the molecular orbital theory calculation for the cheletropic exclusion. As you can see, this molecule ejects the carbon monoxide and the final product is being formed. You have to note, as in this part says, that the bonds to the carbon of the carbon or of the CO are so weak, since the molecule is high stained, that they don't appear at all in this calculation. As you can see, this molecule with this carbon and the CO, the bond, right, is very weak. It means that this reaction is very favorite. As you can see, there is almost no activation energy. Which means you must zoom this part to see that there is a quite difference from this. From the initiation and the activation energy is only 1.4 kilocalories per mole, because the molecule is so stained. This means that this reaction will occur spontaneously at room temperature. And as you can see in the green arrow, this is a very exothermic reaction. It means minus 46.7 kilocalories per mole. This reaction is favored with a heat ejection as the product is being formed. Here we explain the experimental procedure. First, you need a 25 milliliter round bottom flask, and you need to add 0.5 grams of tetraphenylcyclopentadienone, 0.5 diphenylacetylene. Heat strongly using heating mantle for 15 minutes while stirring with a glass rod or spatula. Remember that the activation energy for the first cyclation is high, so you need to heat in order for this reaction to happen or to occur. Then you need to add 10 milliliters of diphenyl ether and stir while it is warm until solution looks homogeneous. Cool solution to room temperature. Add 20 milliliters of mixed hexanes. Cools the solution in an ice bath and collect the product via vacuum filtration. Now there are some practical considerations that you must need to take into account while making the experiment. Because of the high activation energy for the first step, this reaction requires much heat. Use caution because your glass well will be quite hot. Also, clamp your flask and place a ring clamp under your heating well so that it can be lowered when you need to cool the reaction. This is very important. This is clamping Your flask will protect you against burning your hands. That's why you need to do this. The procedure calls for use of a glass stirring rod, but a spatula can be used if the glass rod is not available. But you still need to be careful to not poke a hole through the flask. The diphenyl ether will help bring the reaction to completion by keeping everything in the solution. The solvent is diphenyl ether. This compound is usually a solid at room temperature, and usually the source bottle must be gently heated to melt the solid into order to measure out the solvent for the reaction. And in this case, if you will do that, your TA will do this for you. Hazards. It's very important to study the precautions that you must need to take in case that some reagents or products are dangerous for your health. So in this specific reaction, since it needs to be heated hot, there is more than one fire danger. When one adds the diphenyl ether, use care, as this can be inflammable if the flask is too hot. Remove the flask from the heating well before adding the diphenyl ether. This will prevent that there is a fire or in your reaction. Be specifically careful about adding extents. Make sure the reaction has been cooled to room temperature before you do that. When cooling your flask in ice, let it cool first before placing in ice. Pirate glass can withstand a large thermal shock, even up to 160 Celsius degrees, but it can sometimes break if the thermal change is too fast. So make sure that it is at room temperature before putting it in the ice bath. Those precautions must be taken in this case. And finally, the spectroscopy for the hexaphenylbenzene is, as usual, you need to obtain the IR spectrum and use the minimal sample possible, as it may not be possible to recover this. Obtain a proton NMR spectrum and recover your sample by putting it in the solution onto a wash glass and allowing the chloroform to evaporate. Finally, you also need to obtain an UV visible spectrum in chloroform. That's all that we have for today's experiment. I hope you understood and I clarify as much as possible all the key aspects in this experiment. As always tell you, if you have any doubt or concern regarding this experiment, you can always contact me through my email. I hope you have all a great week. See you soon.